My name is Humza Syed, and today I'll be presenting on analysis of wide and deep echo state networks for multi-scale spatiotemporal time series forecasting. So in this talk, I'll first introduce what a basic echo state network structure is like, and then I will talk about the impacts of adding breadth and depth to these networks. Further analysis is done through the use of evaluation metrics, which will be described later in this presentation. So what are echo state networks? Echo state networks are feed-forward recurrent neural networks that utilize reservoir layers. Reservoir layers are just recurrent layers that utilize fixed random weights. And through these reservoir layers, we take an input temporal sequence projected from a lower dimensional space to a higher dimensional space. This allows for the input to be integrated over time. With these networks, training only occurs on the output layer. What we do is we take the output from the reservoir here and then leave all other weights in the network randomly fixed and train using the Moore-Penrose pseudo-inverse. This allows for a computationally light paradigm for training. So why would we want to add depth or breadth to these networks? So echo state networks have shown before that they perform well on small spatiotemporal tasks given their random structure. However, for more complex tasks, they underperform. Therefore, research has shown through the use of depth and breadth, we can actually extract more complex temporal features as well as more local distinct features or diverse features through the use of breadth. For example, the deep ESN by Galicchio et al., what they do is they hierarchically stack reservoirs like a deep neural network and show that for a more complex temporal task, they actually outperform a baseline echo state network. What's happening is that they're taking the output from the last reservoir here while leaving all other network weights random and just training on there again using the Moore-Penrose pseudo-inverse to solve least mean squares there. So what we do in our work is we extend on the deep ESN. What we do is we add breadth and depth to this network as well as modular connectivity through sparsity parameters for each weight. We also additionally employ the use of intrinsic plasticity to fit the reservoir's dynamics metrics towards a Gaussian. What this does is it decreases the error for the network overall. Now, training in this network, it occurs by taking the output from each reservoir layer through each reservoir pathway breadth-wise, and then the output from the last layer depth-wise, and we concatenate it into a state matrix chi of S, which is then trained. Through this training measure, again, is through the Moore-Penrose pseudo-inverse to train the weights. So to evaluate the dynamics of this of the reservoirs in this network, what we do is we use two metrics. Namely, the first metric is the maximum Lyapunov exponent. So in these reservoirs, there's very random dynamics that are occurring. So what this metric does is it measures the rate of separation between each reservoir neuron, and then it's used as an indicator of what the reservoir's dynamical state is, whether it's closer to a more chaotic state or more of a stable attractor state. Ideally, when the reservoir is in a more in-between state, known as like the edge of chaos, the reservoir has been shown to be in a more ideal performance measure. So how this maximum Lyapunov exponent, or MLE, is calculated is we take the logarithmic mean of I sub k, which is the modulus of the eigenvalue of the kth reservoir neuron for each reservoir. This is averaged across all time steps for each reservoir, and so we get the MLE lambda of max. What this shows us is, let's say our reservoir has a lambda max of closer to a negative number. This indicates that's closer to more of an attractor state or stable state. While if it's positive, it's more of a chaotic state. Once again, when the reservoirs closer to and in between of the attractor and chaotic state in the edge of chaos. This is, again, an ideal reservoir that has been shown to increase performance of the network. We also employ the use of separation ratio graphs, which takes the Euclidean distance from an input to the reservoir's dynamics and its output vector. Taking these Euclidean distances as a ratio, we plot the distance points on this graph. And in this case, when the distances are closer to a y equals x state, again, this is closer to an edge of chaos state, which is ideal for the dynamics of a network, such as these reservoir layers. We test this on two temporal tasks, namely the Mackey-Glass time series dataset and the Melbourne daily minimum temperature series, as both of these present variable nonlinearity at multiple timescales. And we show that for our modular deep ecostate network, with the use of breadth and depth and the heterogeneous topology that it can create, we show that in both cases for the Mackey-Glass and Melbourne, we show that it's competitive for the Mackey-Glass case comparatively to other ecostate networks, and it actually outperforms others for the Melbourne prediction set. One thing to indicate, though, is that the use of intrinsic plasticity plays a large role, as well as the breadth of the network, adding to the local distinct features learned from the input. We also do additional analysis through the MLE and separation ratio graphs, which for just the Melbourne case, due to time constraints. We show heat maps here where as the depth of the network increases to 8 layers deep and a breadth-wise 3, the MLE is actually shown to grow closer to 0 instead of going towards a more chaotic or attractor state. This is also more loosely correlated to the mean absolute percentage error, but is not as correlated for both root mean squared error and normalized root mean squared error. We show that plot here that the MLE versus MAPE, that it decreases as both the error and the MLE grow. The MLE grows closer to the edge of chaos, and the MAPE decreases towards a error that's closer to 0. We also show that for the MAPE that depth and breadth, again, play a major role in decreasing the error closer to 0. And now I show here the separation ratio graphs. So if we're given a network, the best performing one for the Melbourne dataset, there are 4 reservoirs. 2 breadth-wise for 2 reservoir pathways, and then 2 layers depth-wise. So if we take the input through any of these reservoirs, we can see that the input isn't as separated when correlated to its output. However, when we take the output from the first reservoir and push it through the second reservoir, it's closer to the state here where it's the edge of chaos, which is the ideal case. Again, since this is a dynamical network, the edge of chaos is the ideal state for the performance of these networks for a spatiotemporal task. In conclusion, so we introduce a network, ModDPSN, Modular Ecostate Network, which utilizes both breadth-wise and depth-wise to expand on the ecostate network paradigm. Through its hierarchical connectivity, we extract more features from the temporal input, and then through these dynamics, we can show that there's a correlation between the MLE and the percentage error, which can show how the dynamics of a reservoir can actually be used as an indicator of how the network can perform when using these random dynamics. References.